It's never been anything but that balance, and we've complicated it with a lie.
Conspiracies keep unfolding one after another. And at the center of it all lies a burning question: what truly defines our universe? To find the answer, we must dive into the tiniest building blocks of existence, particles that govern everything around us. Physics isn't just a subject. It's the ultimate key to unlocking the mysteries of reality. At the heart of this pursuit is CERN, the world's largest particle physics laboratory. Here, scientists continually push the boundaries of what we know, from discovering how gravity interacts with antimatter to precisely measuring the elusive Higgs boson. But what if a discovery changes everything we thought we knew? Join us as we uncover a shocking revelation recently shared by CERN, a revelation that could reshape our understanding of the cosmos. CERN, the European Organization for Nuclear Research, was established in 1954 and is headquartered in Meyrin, Switzerland. Since its inception, it has played a crucial role in expanding humanity's knowledge of the universe. Founded after World War II, its mission was to foster scientific cooperation across Europe. One of CERN's first major milestones came in 1957, with the construction of a 600 mega-electronvolt synchrocyclotron, the SC, its first particle accelerator. Though modest by today's standards, it opened the door to revolutionary research in particle and nuclear physics. One early breakthrough was the confirmation of the decay of the pion particle into an electron and a neutrino, observed just hours after the experiment began. This single discovery propelled CERN into the international spotlight. In 1959, CERN launched the proton synchrotron (PS), a more powerful accelerator that allowed deeper exploration of high-energy particle interactions. Then, in 1967, CERN introduced SOLD, a facility for studying radioactive ions. This expanded CERN's impact into various fields, including astrophysics, medicine, and nuclear physics. One of the most groundbreaking achievements came with the creation of the intersecting storage rings (ISR) in the late 1960s. These rings allowed two proton beams to collide head-on for the first time in 1971, marking the birth of the Hadron Collider. Why was this revolutionary? Because smashing particles into each other rather than into a stationary target produced far greater energy interactions. This method paved the way for future advances, including a technique called stochastic cooling, still vital in modern particle accelerators. The ISR laid the foundation for CERN's most ambitious project to date, the Large Hadron Collider, LHC. The LHC is the largest and most powerful particle accelerator ever built. With a circular ring stretching 27 kilometers underground, it's located at the CERN facility near Geneva. But what does it actually do? At its core, the LHC is a collider. It accelerates particles, typically protons, to nearly the speed of light and then smashes them together. This replicates conditions that existed just moments after the Big Bang, giving scientists a glimpse into how the universe was born. Why is this important? Because to truly understand the universe, we must understand the fundamental particles and the forces that govern them. Inside the LHC, two beams of high-energy protons race in opposite directions, reaching speeds of 99.9999% the speed of light. These speeds are achieved using radio frequency cavities, which generate alternating electric fields to continuously boost the proton's momentum. But with such velocity, why don't the protons shoot off in a straight line? Here's where the LHC's brilliance shines. Protons, like all charged particles, naturally travel in straight lines unless acted upon by an external force. To keep them moving in a circular path, the LHC uses powerful magnets to bend their trajectories. These magnets don't accelerate the protons, they steer them. And to do that, they generate magnetic fields as strong as 8 Tesla, over 200,000 times stronger than Earth's magnetic field, which is just 0.04 Tesla. To reach this level of magnetism, the LHC's magnets must operate in a superconducting state, which eliminates electrical resistance. That requires cooling them to an astonishing -271.3 degrees Celsius. Massive detectors are positioned at 4 key locations along the Large Hadron Collider's circular ring, right where the two proton beams collide. It's here that the real magic happens. As these high-energy protons smash into each other, they shatter into hundreds of new particles. These aren't just any particles, they are the fundamental building blocks of our universe. But finding them is no easy task. The particles created in these collisions exist only for a fleeting moment before decaying into something else. To capture these brief phenomena, CERN has developed some of the largest and most sophisticated detectors in human history. The two biggest detectors, ATLAS and CMS, are designed to gather an immense variety of data from every single collision. Then there's ALICE, which focuses on studying quark-gluon plasma, an exotic state of matter that likely existed moments after the Big Bang. And finally, there's LHCb, whose goal is to uncover the mysteries behind matter and antimatter and perhaps explain why the universe is filled with matter when equal amounts of antimatter should have also been created. Together, these four detectors, ATLAS, CMS, ALICE, and LHCb, form the very core of the LHC's scientific mission. They help us explore everything from the tiniest components of matter to the very structure of space and time itself. But the LHC doesn't just accelerate particles to near-light speeds. It also gathers an enormous amount of data from each collision. This data is essential to solving the deepest questions about the universe and has already led to discoveries like the Higgs boson. The Higgs boson, sometimes called the God particle, the Higgs boson was confirmed in 2012. It's a particle that gives mass to all other particles, a key piece in understanding how the universe works. But finding it was no small feat. You see, the LHC produces nearly 1 billion collisions per second. That's right, 1 billion. The real challenge isn't just recording this data. It's sifting through all of it to identify the rare, fascinating events buried deep within the noise, the ones that could unlock secrets never seen before. Let's look closer at ALICE and LHCb, experiments that perfectly represent the variety of studies at CERN. ALICE dives into the study of quark-gluon plasma, the same type of matter that existed just after the Big Bang. This plasma is made of quarks and gluons, the particles that eventually bind together to form protons and neutrons. ALICE tries to recreate and study this primordial soup to better understand how the early universe evolved. At the same time, LHCb is exploring a question that has puzzled scientists for decades. Why is there more matter than antimatter in the universe? According to theory, the Big Bang should have produced equal amounts of both. Yet here we are living in a universe dominated by matter. By studying the subtle differences between the two, LHCb hopes to uncover the reason for this imbalance and possibly the origin of our entire existence. But these experiments demand more than just powerful detectors. Processing the insane volume of data generated by the LHC requires incredibly advanced systems. With 1 billion proton collisions every second, more than 99.9% of that data is irrelevant. Only a tiny fraction holds the keys to groundbreaking discoveries. That means the detectors must instantly and accurately decide which events are important enough to keep. To put it in perspective, the LHC records about 1 million terabytes of data per day. That's enough to fill over 300 modern 1 terabyte SSDs every single day. And gathering this data is only the beginning. The real work starts when scientists analyze it, hoping to find something extraordinary. It's like searching for a needle in a haystack made of data. Take the search for the Higgs boson, for example. Scientists needed to spot extremely subtle signals that could easily be lost among the chaos of particle debris. So how do the LHC's detectors recognize what's valuable? They use some of the most advanced technologies ever created, systems that track particles with astonishing precision. Let's take a closer look at the CMS experiment, one of the most complex detectors at the LHC. It's made up of multiple subdetectors, each with its own purpose. The tracker follows the paths of charged particles. As these particles pass through the thin layers of silicon, they leave tiny traces behind. These traces are then reconstructed to map out the particle's trajectory and origin. Then there's the calorimeter, which measures a particle's energy. Made of lead tungstate crystals, the calorimeter captures the light emitted as particles pass through it. The amount of light reveals the particle's energy, helping scientists understand its identity and role. Together, the tracker and calorimeter, along with other instruments, build a detailed picture of what's happening in each collision. From this picture, scientists search for patterns, clues, and anomalies that might point to something new, something revolutionary. These tools, experiments, and processes are all part of one goal: to understand the universe from its smallest particles to its greatest mysteries. The real work begins once the data is collected. To detect the Higgs boson, scientists knew they had to search for a very specific signature, one left behind by the particle as it decays. Almost instantly after it's created, the Higgs boson breaks apart, often transforming into two photons or particles of light. Inside the detectors, these photons have a very distinct signature. They create a flash of light in the calorimeter but leave no trace in the tracker. That's the key clue. However, distinguishing Higgs boson photons from the countless others produced during the collision is a massive challenge. To separate the signal from the noise, scientists examine characteristics like the energy and direction of each photon. Generally, photons from Higgs decay behave differently than those created by other processes. That's where advanced algorithms come in, filtering through billions of interactions to pick out the rare, meaningful events. And this meticulous analysis paid off. After decades of searching, the Higgs boson was finally discovered, redefining the boundaries of physics. But the story doesn't end there. Each year, the LHC's experiments generate an astounding 15 petabytes of data. Just 1 petabyte equals around 250,000 movies, and over the years, the LHC has accumulated over 200 petabytes of data. This vast archive continues to fuel groundbreaking discoveries. One such discovery is evidence for quarks, the fundamental particles that make up matter itself. These quarks come in different flavors, and the way they interact is essential to the universe's structure. But many types of quarks, especially the heavier ones, are extremely unstable and decay in a matter of trillionths of a second. Take the beauty quark, for example. It lives for only 1 to 2 trillionths of a second. Yet within that brief existence lies valuable information about the deepest structure of reality. New data from the LHC has started to challenge long-held beliefs about how quarks behave. According to the standard model of physics, when quarks decay into particles like muons or electrons, they should follow predictable patterns. But here's the twist. The observed decay rates into muons differ from what the theory predicts, especially when compared to electrons. This anomaly hints at something extraordinary, the possibility of unknown forces at work, pushing us beyond the limits of the standard model. Now, the standard model has long served as the cornerstone of our understanding of particle physics. It explains 3 of the universe's 4 fundamental forces: electromagnetic, strong nuclear, and weak nuclear. But it leaves 2 critical mysteries unsolved: gravity, and the invisible yet dominant force we call dark matter. Because of these strange quark decay results, some scientists now theorize the existence of a new force, one that interacts subtly with electrons and muons. They speculate about an energy carrier particle, possibly a variant of the Z boson so elusive that it hasn't yet been discovered. If proven, this discovery could expand the standard model and offer powerful insights into long-standing cosmic questions, from the nature of dark matter to the deeper role of the Higgs boson itself. These are not just theoretical puzzles, they could be the missing pieces that lead us to physics' ultimate prize, the unification of all fundamental forces under a single, elegant framework. For decades, scientists have chased this theory of everything. And now, with each collision at the LHC, we move a step closer to unlocking it. That's why the LHC remains the most powerful particle collider on Earth, supported by over 10,000 researchers and hundreds of institutions across the globe. This is a global mission to push the boundaries of human knowledge. And the discoveries keep coming. In a stunning breakthrough, CERN scientists have made history by detecting high-energy neutrinos created within the LHC for the very first time. These ghost-like particles, which barely interact with matter, were observed with remarkable precision. 53 neutrino interactions were recorded, a major milestone in the world of particle physics. This could help unravel some of the universe's most mysterious phenomena, like the powerful neutrino interactions inside star cores, or the explosive forces that fuel supernovae. Neutrinos, practically massless, chargeless, and invisible, move through space by the trillions, passing through your body, Earth, and everything in it almost entirely undetected. And yet, by finally catching a glimpse of them, scientists may gain a new window into the most hidden mechanics of the cosmos. This is the future of physics, a new era of discovery, and it's just getting started. Every single second, around 100 billion neutrinos pass through just 1 square centimeter of your body. Yet you don't feel a thing. Why? Because neutrinos are some of the most elusive and mysterious particles in the universe, so ghostly in nature that they barely interact with anything at all. That's why they've earned the nickname ghost particles. These spectral travelers are created in various powerful and natural ways, from the fusion and decay of atomic nuclei to radioactive disintegration, cosmic ray interactions, and even inside nuclear reactors and particle accelerators like the LHC. They're even produced in everyday things like the decay of potassium in a banana. Neutrinos are everywhere, but they're infamously hard to detect. Their ability to pass through entire planets without leaving a trace makes them both frustrating and fascinating to scientists. Since their first detection in 1956, when they were spotted escaping a nuclear reactor, researchers have been chasing these ghost particles for decades. And in 2021, a major milestone was reached. For the first time in a collider experiment, scientists confirmed 6 neutrino interactions, undeniable proof of their existence inside a high-energy environment. But this confirmation didn't come easy. It required 2 more years of exhaustive investigation and analysis to verify. James Boyd, a particle physicist at CERN and co-spokesman for the Phaser project, described it as a huge leap forward. According to him, the discovery of high-energy neutrinos at the LHC opens the door to a whole new class of exploration, one that could unlock the secrets of the most extreme environments in the universe. Neutrinos could help explain how stars burn, how they explode into supernovae, and how they release immense amounts of energy and particles into the cosmos. They may also be the missing link in understanding black holes, gamma-ray bursts, and other strange cosmic phenomena that have long defied explanation. The LHC's ongoing experiment will continue gathering data until the end of 2025, and physicists believe that the next few years could bring unprecedented discoveries. With every new interaction observed, we inch closer to understanding the deeper mechanics of the universe itself. And yet, as science moves forward, a darker mystery begins to unfold. Subscriber pick of the day: deep inside the CERN control room, Dr. Elena Hartman stood frozen. Her eyes were locked on a flickering stream of data. Something was off. A new particle had appeared in the collider's data, one unlike anything they had ever seen. It was flickering in and out of existence with unpredictable energy, behaving in a way that defied all known laws of physics. Could it be? She whispered. This wasn't just a new particle. It exhibited strange, gravity-defying behavior, as if it came from a completely different realm of reality. Soon, the entire CERN team was alerted. Simulations ran non-stop, data was verified, and theories began to form. Then came the moment the world would never forget. Dr. Michael Adler, the lead physicist, called for an emergency press conference. And what followed stunned the world. Scientists at CERN revealed that what they had found was not a mistake, not a malfunction. It was evidence of a parallel universe, governed by completely different physical laws. For the first time in human history, scientists were on the edge of discovering the true fabric of reality, and the multiverse was no longer just a theory. As the world watched in awe, Dr. Hartman stood in disbelief. What would this mean for humanity's future? But outside CERN's walls, another story was brewing. The news ignited a firestorm of conspiracy theories. People began to question the safety of the LHC all over again. This wasn't new. Ever since its inception, the Large Hadron Collider has been the center of wild theories and doomsday predictions. One of the earliest and most notorious claims was that the LHC would create a black hole large enough to swallow the Earth. The idea was based on the belief that colliding particles at near-light speed could accidentally form a singularity. Yet, nothing of the sort ever happened. CERN spent years debunking the panic, releasing scientific reports to assure the public that the collider posed no existential threat. But that didn't stop the rumors. In the early 2000s, things took an even stranger turn. A new theory surfaced, one that blamed delays and malfunctions at the LHC on time travelers from the future. The idea was absurd yet persistent. A visitor from another time, trying to sabotage the collider to prevent it from unlocking something catastrophic. The most bizarre detail? A baguette-carrying bird was allegedly involved in the sabotage, a bird that somehow managed to interfere with critical equipment. To some, it was just a joke. But to others, it was confirmation that CERN was playing with forces beyond human understanding. As the LHC continues to operate, accelerating particles and smashing open the secrets of the cosmos. One thing is certain: the line between discovery and danger, fact and fear, continues to blur. One of the core beliefs fueling conspiracy theories about the Large Hadron Collider LHC is that its immense power could potentially trigger a catastrophic event. While the details of these claims are far-fetched, the LHC has long been surrounded by bizarre speculations, some even stranger than the concept of time travel. One of the most widely circulated theories suggests that CERN is secretly opening portals to other dimensions or even to hell itself. These rumors gained traction when CERN publicly stated that it was experimenting with creating miniature black holes to explore the nature of antimatter. For many, the idea of forming black holes, no matter how tiny, sparked fears about tearing open gateways to unknown realms or parallel universes. Despite these theories, CERN continues to push the boundaries of particle physics. The discovery of the Higgs boson in 2012 was a groundbreaking achievement, yet it left us with many new questions. How exactly does this particle influence the fundamental forces and the structure of matter that make up our reality? Could it help explain the universe's strange imbalance between matter and antimatter, or even shed light on the mysterious substance known as dark matter? These mysteries are exactly what the Future Circular Collider, or FCC, is designed to investigate. As the proposed successor to the LHC, the FCC aims to unlock new levels of energy and precision, offering scientists unprecedented insights into the universe's deepest secrets. Currently, researchers are conducting feasibility studies for the FCC, weighing technological challenges, financial requirements, and environmental impacts. But the bigger question remains: could CERN's ongoing research one day provide the answers to some of the greatest enigmas in existence? From the origin of the cosmos to the invisible forces that govern it all, the next chapter in our journey into the unknown may just be beginning.